Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So the internet is divided into regions owned by different ISPs, and the relationships based on which they carry traffic for each other are based on contractual obligations. These contractual obligations determine how ISPs treat each other and how they carry traffic for each other. But in general, these contracts tend to be very simple in terms of monetary exchange. For instance, two large ISPs would get together and say, I'll carry traffic for you and you carry traffic for me for free, as long as our traffic I send you and what you send you is within a certain bound, which tends to be a factor of 2 or so, a very loose bound on that. So getting into competing interests. So one direct effect of that is that ISPs tend to make selfish routing decisions. So for instance, this blue ISP, while routing packets, would want the flow to get out of its network as soon as possible to reduce the resource consumption in its own network. And in doing so, it's unaware of, or it does not know or does not care that the length of the flow or length of the path of the flow has actually been elongated. A twist on the same thing is today there are mechanisms in the internet that enable not only the senders of the flow, but also intermediate nodes and receiver nodes to control where the flow comes in. But there's no mechanism for them. There's no mechanism in the system that enables them to do so jointly. So it's kind of like siblings fighting over like a TV remote, that either one of them has it or the other one does not, and then you can fight over. There's no way for them to cooperate and decide, okay, both of us like this path, let's take it. So it's like unilateral control by one party. An impact of ISPs being independent businesses is they have different notions on how to run their network, how to maximize their profit based on what they think their customers want. So the system's impact of that is they're optimizing their networks for different things. Some of them might be optimizing for distance. Other networks might be optimizing for congestion, that I want minimum congestion. So already a task of optimizing this network has become harder because different parts of the network are being optimized for different things. Finally, the third competing interest here is that ISPs have an interest in hiding information from each other, which is to say that there are competitive concerns in the system. For instance, if AT&T, one ISP, knows the cost for Sprint for carrying traffic, let's say from San Francisco to Seattle, and AT&T happens to know this is a very profitable route for Sprint, what it can do is provision its networks to undercut Sprint's performance, or Sprint's profits at least. So today in the routing protocols, the information that is exported across ISP boundaries is just what's the high-level path in terms of what the sequence of ISPs are to reach a particular destination. So the orange ISP would tell this blue ISP that you can reach D through me and followed by G. So no sense of the quality of the path itself is exported, and which is why you see a lot of selfish path selection going on, because at some level there's no information available. So to summarize, the competing interests I talked about were selfish routing, independent optimization criteria, and very little information flowing across boundaries here. And these consequences, like these competing interests in the internet today, are largely unmanaged, which has consequences today. And I've measured some of those in my earlier work. In particular, I found that paths can be inefficient and unstable at times. This I found in a global study of internet routing paths. The interesting thing here is, in terms of these behaviors, I'll get to examples of these in a minute. But in terms of these behaviors, the common case is often fine. It's not the case the internet is completely broken. The internet mostly works. But the interesting reason why the common case is fine, that ISPs are actually designing their networks around the shortcomings of the protocol, instead of us designing protocols to suit their networks. But this network design process is not sufficient by itself to take care of all the weird cases that arise in practice. And when that happens, operators have to manually configure their routing. In fact, this manual process, from a systems perspective, again, you would imagine this manual process is very error prone. In a study of global configuration errors, I found 75% of new routing announcements in a day result from misconfiguration, somebody making an error someplace. And this manual control also involves sometimes ad hoc cooperation between operators. This is like manual cooperation on the phone, which kind of drives up the cost of running these networks also, because now these ISPs have to pay these routing experts a huge amount of money. There's some anecdotal evidence that a third to a half of large ISP's operating budget goes towards the salaries of these experts that they have to hire. In the next 3 slides, starting from this one, I'll try and give you a sense of what kinds of things go wrong. Starting with this idealized example of 2 ISPs that interconnect in 3 places. And I'll talk about flows that go from that dot to that dot in that ISP. So what happens is when ISP, the blue ISP wants to route to the orange ISP, it picks a locally optimal interconnection point. Even though this path is better in terms of distance, it restricts itself to this path, taking a selfish decision. The orange ISP does the same, taking the top interconnection. Now the interesting thing about this example is the following, that compare the solid routing pattern with the dashed routing pattern. What's going on in the process is that both ISPs are actually suffering. By that I mean the cost of carrying this blue flow and this orange brown flow here is a lot less than this plus this. But there's no mechanism today in the internet that enables ISPs to reach this particular operating point. So they each continue routing selfishly the way they want, but in the process both of them are hurting. It's not the case that we are not only worried about the overall path length, but the fact is that both ISPs are losing is the point to take away, Sharath. No, you can't. Because what MEDs do, MEDs also select locally optimal path, but the definition of local changes. The definition of local becomes the receiver of the traffic. So if MEDs were being used here for this blue flow, let's say the orange was exporting MEDs, this path, this blue flow would actually take the top link, not the middle link. There's no compromise, there's no mechanism for compromise available in MEDs as they're implemented today. If I'm announcing MEDs to you, so for instance, if you assume that higher MEDs are, sorry, let me bring everybody into the conversation. So internet routing has so one of the mechanisms by which the receivers control traffic today are called MEDs or multi-exit discriminators. And the way the MEDs work is the following, that the receiver ISP would announce that this is the best path for me, this is the second best path for me, this is the third best path for me for receiving traffic to this particular destination. And the way it works is when the senders are sending traffic, if their MEDs are contractually supposed to be honored, would pick an interconnection that is best for the receiver, right? So based on that, this blue ISP would actually take the top link, not the middle link. So MEDs are still locally optimal. They don't allow any sort of compromise between ISPs. Does that answer? Okay, cool. So this problem that I described in the case of two ISPs, what I found is that it's actually much worse once you bring in multiple ISPs into the picture. Because every ISP along the way is taking decisions selfishly. At the same time, it's much worse when you talk about multi-continents or intercontinental paths, because the inefficiency that arises from this pattern is dependent on how many interconnections ISPs have. And intercontinental paths usually don't have that many interconnections. As a result of the cost of taking a suboptimal decision is a lot higher. In the next two slides, I'll quickly describe two examples. These are real-life measured examples rather than idealized examples. And it goes to show that bad things happen even though we have operators working hard at the problem. So this incident I measured in about 2003 on the west coast of the US, and it involves two of the largest ISPs in the network, AT&T and Sprint. And the interconnections were Seattle and San Francisco. So here was a traffic pattern that should have happened if AT&T was sending traffic from San Francisco to Sprint San Francisco and Sprint Seattle. It's taking a locally optimal decision, which in this case also happens to be optimal from a path length perspective globally. But there was an overload inside the AT&T network here. So what AT&T does to avoid this overload, shuttles some of the traffic up there. But note that AT&T has no information about the Sprint network. So what it ended up doing was shuttling traffic up to Seattle, and this traffic was coming right back to San Francisco in this particular example, because again, AT&T knows nothing about the Sprint network. And just like last example, there is a routing pattern in the system, this dashed one, which actually benefits both AT&T and Sprint if they were to cooperate with each other. AT&T's customers would see a lot better performance. Sprint reduces its network consumption, and its customers see a better performance in the system. This example is actually my favorite. It's adapted from an incident that happened between two large ISPs in Europe. And so here's a simple example of what went wrong. So they were interconnecting in three places. This link broke. The blue ISP shuttled the traffic using some locally optimal decision, both of those flows, to the bottom link. But this kind of caused an overload inside the orange ISP, and the blue ISP could not have prevented it based on information it had. What the orange ISP does, takes one flow and shuttles it to the top link. But again, orange ISP ended up causing overload inside the blue ISP by this decision. It couldn't have prevented that based on today's mechanisms. So the blue ISP noted it, brought the flow right back. The orange ISP noted it, brought the flow right back up. And this actually went on for 2 days. These operators were manually configuring their routing. Every 30 minutes, they'll change the routing. They'll see, okay, they'll make a change. Oh, it works now. But the other operators would say, oh, no, network's broken again. Let me make the change again. So every 30 minutes, they were doing that. Finally, they figured out something must be horribly wrong. And they called the other ISP, and they figured out what's going on. And after 2 days, they had to like manually negotiate what the solution would be. Yes. Yes.
Okay, because in that situation, there actually is a negotiation mechanism.
Which is the telephone. The thing is, do you want that, or do you want something better?
Well, it would be better if we did, but what's amazing is that even when we have it,
Yes. I mean, they didn't realize the problem for 2 days, because most of the problems, once they fix the routing, most of them go away, and some corner cases remain, which. But anyway, so the point about this example is that even if the ISPs were trying to do what's best for them and their neighbors, there's very little mechanism today that helps them to do that. Yeah? Social networking. This one is social networking. The previous example is actually a measured one. We measured it in our SIGCOMM paper, and we report, and we actually verified that there was congestion along the link. So that's a measurement study. And this one is from hanging out with ISPs and operators and telling them about your work. So they tell you, oh, this could have fixed that, or something similar. So that ends the part of my talk where I was going to try and explain competing interests in the internet. And I also described a few examples how things can go wrong and what kinds of bad things happen. And hopefully the common thread that I wanted to get across was that that the problems I described, in some sense, are not a fundamental consequence of the competing interests. And the reason I say that is because of that, both ISPs are losing today. And if we give them practical protocols for cooperation, they are likely to do so. And which is also kind of evident in the fact that they do cooperate today using ad hoc mechanisms, which is the phone network. When your data network breaks, you use the phone network. So here's a hope. So if we can give them some practical protocols, that they'll cooperate. And the next part of my talk, I'll try to describe my approach and my design of such a practical protocol in the system. So I'll motivate my approach in the context of the 3 ISP interests I described, because like I said, my approach or the protocol has to be mindful of the ISP interest. So you can think of each of these as a design goal we have. The limited information disclosure, independent optimization criteria, and win-win outcomes. So limited information disclosure is ISPs don't want to tell each other a lot of sensitive information for competitive concerns. This includes information on topology, performance, and monetary cost of running the network. Independent optimization criteria basically says that there is no universal optimization criteria. So we're not designing a cooperation mechanism that focuses just on distance or that's focused just on minimizing congestion. So now the interesting thing to note about these two things is, once you bring these two into the picture, the standard approaches we know of route optimization actually go away. For instance, we cannot compute the socially optimal for 2 reasons, because socially optimal requires that ISPs have the same metric. At the same time, socially optimal requires that ISPs be willing to share that information. And people in the audience who are familiar with mechanism design approaches would also note that these two are kind of in conflict with standard mechanism design approaches too, because those approaches also optimize for a certain metric, and they require information disclosure too. So to tackle these 2 concerns, what I say, okay, let the ISPs use agnostic cost. By agnostic cost, I mean these costs are agnostic to the exact metric used. ISPs, while displaying or disclosing these costs to each other, map their internal optimization criteria to this agnostic cost. For other ISPs, it's just a number. I give you 10 and I give you 5. All you know is 10 is worse for me than 5. You don't know what my criteria is, and you don't know how I obtain those numbers. Sorry? They are linear, yes. I get to an example in here. The third criteria is win-win outcome, which is coming from the selfish nature of ISPs, that we want a cooperation mechanism using which all of the ISPs win. And the reason for that is simple. If the cooperation mechanism does not guarantee that all ISPs are winning, the ISPs that lose will simply not cooperate, and we go back to the world we have today. And the result of that, the implication of that for us, is that we need to compensate ISPs that lose. So how might we compensate? Let me step back a minute. The reason we need to compensate is because flow paths today are locally optimal. So if we try and move any one flow to any other path, it hurts at least one ISP. So if we don't do it right, there would be cases where ISPs actually lose. So how can we compensate ISPs? So one way of doing that is to use money. But like using real money, it's like operators and ISPs really shudder at the thought of using real money in terms of routing, and the reasons are legitimate actually. One is they don't want to tell each other anything about the real cost of running the network. The other is it's not even clear that ISPs can actually compute real money in terms of sending a bit from Seattle to San Francisco. And the third reason is it kind of goes counter to simple monetary exchange or simple contractual practices they have today. So I'm going to rule out that monetary exchange is too complicated a solution for our domain, and I'll instead propose that ISPs should barter instead, and that ISPs should take a more holistic view of the overall relationship of the flows they exchange and let them barter on some flows and let them lose on others. And here's what I mean by barter. And this is, I'm going to explain quickly an example of barter with two ISPs using agnostic costs. So same example that I showed earlier on. Let's say the blue ISP cares about minimizing the number of router hops in its network. So it can simply get these agnostic costs out of it. The units have been taken away, and let's say there's a one-to-one mapping. Similarly, let's say the orange ISP cares about the distance in milliseconds in its network. So it can do the same. Other metrics like link load and link utilization or capacity of the link can also be translated similarly. And to some degree, ISPs do that already today when they optimize their routing internally. So now let's consider traffic today. So these numbers are actually the cost of carrying traffic. So this 1 is coming from here and 11 is coming from here. The cost to the two ISPs, their individual cost of carrying traffic. So the blue ISP would pick the bottom interconnection, locally optimal decision. We might want it to pick the middle interconnection, but it has no incentive to do so because it kind of loses in that process. So that's not going to happen. The orange ISP does something similar, and these numbers again, this is 1 plus 7 is 8, and 11 plus 1 is 12, the total cost of carrying this traffic. Now what we can do actually, look at the cost of the dashed routing pattern, which is 4, 2 plus 2, and 6 here, 3 plus 3. So if we arrange this barter right, what's happening is both ISPs are winning. So we've taken an overall view of traffic, and we've enabled flows to have our traffic to go through better paths in the system, and both ISPs gain. So here's the hope, that both ISPs should be willing to trade losses on some flows for bigger gains on others, and as a result of that, we can optimize routing. And the key thing to note here is not so much that the overall paths are shorter, but the fact that both ISPs are winning. This has two consequences that I'd like to point out. Is basically what just came out, that cost should be linear. Basically what I implied was this 2 plus 2 is better than 1 plus 7. So the agnostic cost that ISPs compute should compose over addition in some sense. The other thing to note is, since these costs are agnostic, we're not optimizing our paths explicitly for any particular goal. Instead, what we are doing is that each ISP is optimizing within itself. And the hope is, with this implicit optimization, overall path length is lower. What it does in practice is rule out most of the egregious behaviors, and such, just as it happens in systems like web caching and stuff. This kind of brings us very close to the optimal, not all the way, just if case these ISPs have comparable metrics. Yeah.
The relationship between whatever ISP gets and the cost detected for the agnostic cost is linear, or is it enough that it's increasing?
So internally, an ISP can do what they want. So you need composition over addition. Otherwise, there's no guarantee that 1 plus 7, the solid routing path, is actually better than the dash routing path, right? I mean, I took this flow and this flow and that flow and that flow. If these costs are not like 8 is more than 4 is what I'm claiming, and that's where like the composition over addition I'm talking about. But I did, in terms of just like disclosing information, I think what you're saying is the difference between ordinal versus cardinal costs. If you actually go over internet topologies and run some real numbers, it turns out there's not much route optimization that happens with ordinal costs. So you need some sort of cardinality in there, both from an ISP's perspective and from a route optimization perspective. Venkat. Yeah. Oh yeah, this is, sorry. So this is so this is exactly what is happening. This is exactly what is happening. So this is cost just within the blue cloud. So 1 is the cost to blue ISP of carrying the blue flow, and 7 is the cost to the blue ISP of carrying the brown flow. So I'm not adding cost across the two ISPs. Oh no.
Where the blue guy said, okay, I'll define flow up to
Okay. Right.
Because that 8 is just confusing because 7 and 1 is there. And right.
Oh gosh. Good. I will. Good point. Sharath.
Are you saying that these costs are going to be fairly static, or that you have seen that the costs are not going to change dramatically depending on where the costs are?
From a practical perspective, yes. I'm not calling for a fully dynamic routing in the internet, and there are reasons why that would not happen. If you study how ISPs assign meds today, they're mostly not link load based. But the other thing to note is that just in terms of the traditional dynamic routing problem, the problem in the internet scale given ISP practice is a lot simpler because links are over provisioned to a large degree. And I can actually talk to you more in detail about that. There's some involved results about like how stable, if they were to do it based on something that changes really fast. But for now, assume that they don't change very fast. Yeah. Uh-huh. Uh-huh.
And I figured out the cost, but then if you're enabling us to change some of those paths in response to that, then is it still the case that those cost metrics are the same? Or are those going to be
Yeah.
cost metrics then?
So the hope is that minimal variations or just small variations would not change whatever your basis of cost is the assumption here once you start dynamic routing. And there are actually there are reasons to believe why that would happen because the links are, so here's what, ISPs are not trying to do a max-min routing over the network. All they want is to some degree that the links are already there. What they want to do is that all of their links stay below a certain threshold. So as long as that congestion or whatever the threshold is fairly comfortable, then they should not lead to massive variation. So for instance, I'm saying that link load going from 10% to 20% would not lead to any cost change. Is that, well, because they don't care as long as it's below 50%. Right. Yeah. Yeah. Something like that. Yes. Yeah.
You mentioned that I haven't talked about what I'm telling you, that's already stored. I actually already tell that these are different things. This is one record. So what you're saying is we want to different metrics.
No, I'm saying the exact information exported is a lot like meds, but I'm going to do a much better job at utilizing that information. Meds are used today, but very selectively, only between customers and providers, for instance. We're actually monetary exchange. They're not used between peers because peers have no reason to give any favors to each other. The other problem with meds is even though information exchange is happening, you're still stuck in that locally optimal unilateral route choices, and which is the other thing that I want to take away from the system. That the meds exported today, most of them don't change dynamically, but the different ISPs have different ways. Internal, they don't. I mean, it's hard to tell what the bases are, but my understanding is meds usually are assigned based on distance within the network or link capacity itself. Like the standard Cisco metric for assigning a cost to a link is inverse of capacity, for instance. So that was barter between two ISPs, which is conceptually straightforward. You can understand what's going on. But what about barter between multiple ISPs? So there are two possibilities how we might arrange barter between multiple ISPs. One is just multilateral barter, that you barter with the whole network as such. And your hope is to gain in the total relationship with the rest of the internet. The other way to barter is to arrange independent bilateral barter, which is much closer to what happens today, that each ISP has an independent relationship with each of its neighbors. And there's a trade-off between the two. Multilateral barter is likely to be more efficient because what it enables an ISP to do to take small losses in one part of the network to bigger gains in another part of the network. But at the same time, bilateral barter is much simpler. It's much simpler to monitor and enforce. And it's for that reason that I chose to basically implement a form of bilateral bartering in the system. And I'll show you in the evaluation part of my apart that this actually does not cause any sort of efficiency loss in practice using realistic topologies and workloads. Venkat. Real money as part of fine-grained exchange of real money, yeah. So I'm going to argue I'm going to argue that multilateral barter is not required actually if you care about route optimization. There is not much more gain to be had from multilateral barter compared to just doing independent bilateral bartering. Yeah, in terms of results. So I mean, so in theory, multilateral barter does let you do more global optimization, but it turns out I think the answer somewhere like why multilateral barter does not bring you much benefit kind of lies somewhere in the nature of the internet topologies and how connected the ISP graph is. Okay, so at a high level, that was my approach. What I'm trying to do is to arrange for bilateral barter between ISPs using the agnostic cost. And I'm going to describe a practical routing protocol that I call Visor to implement this approach. The thing to note is that we want practicality because finally you're designing a system for the internet, so it should scale and it should go to internet scales. Any simple way of arranging barter where ISPs explicitly say, I'll do this if you do this for me, is likely to be very heavyweight. And it's also kind of more susceptible to what happens with dynamic conditions such as flows arriving and going. So I'll describe a protocol that in its structure actually fits very close to the current routing protocols, but yet it tries to achieve bilateral barter in that very structure. And I'll start describing the protocol for the 2-ISP case first because it's simpler to understand. It also brings up a lot of interesting issues that arise in this particular domain. In this limited 2-ISP case, the goal for each ISP is for each flow that they send to pick the interconnection here. So here's how it works. As a first step, the ISPs are announcing to each other. They are basically computing their agnostic cost within their own network clouds independently. Then the downstream ISP, which is the receiver of the traffic, is going to announce what their agnostic cost is to the upstream ISP, which is the blue ISP in this case. As a third step, this is the simple part. As a third step, the upstream ISP is selecting the interconnection based on its local cost and the received cost. So this is the important bit where barter is happening. Barter is basically I compromise for you, you compromise for me. In doing this step, the upstream selecting a link based on both local and remote costs, for instance, by minimizing the sum of the two. It's doing the orange ISP a favor. And the barter happens because the orange ISP is actually the upstream for some of the flows, that both ISPs are upstreams for certain amount of the traffic. So if the orange ISP also selects the links in a way that is sensitive to both local and remote costs, these ISPs are doing favors to each other in the process, and which is where barter is happening in the system.
And here, I think I heard you say you were going to add the blue and orange.
That is one of the ways for, no, so this is just a path. This is in terms of, okay, so this is your goal, that you want to select cost based on both local and remote. At the end of the day, you'll put in some algorithm in the router. One example algorithm is to add the cost. And why it might be right to add the cost, I'll get to in 2 slides. But adding is just adding and minimizing the sum is one of the ways to be sensitive to both the costs. You could use some other metric too in there.
Yeah, I'm skeptical of adding because then the scale of the numbers were different.
I'll actually set the scale right in the next slide. I realize the problem with the scale. So that, yeah. Okay, so adding is a little bit deceptive. What's happening here by adding across all flows? So adding is just a mechanism. You can think of some other mechanism for being sensitive. What's happening eventually is that the blue ISP or the orange ISP measures the cost the blue ISP is causing it by adding its own numbers. So let me step back. So don't think of it as adding. It's blue ISP is picking paths based on some criteria that kind of is sensitive to the concerns of the orange ISP too. And adding is just one of them. At the end of the day, you add cost within the orange ISP of all the traffic that goes from the blue ISP to the orange ISP. The total cost within the orange cloud has been minimized or has been reduced compared to just selfish routing.
Now another question here, the concept of the amount of traffic.
Sorry?
I mean, one task might be carrying a little traffic, another task might be carrying a lot of traffic.
So assume these are per byte. Yeah, so all of these things would actually become clear in the next 2 or 3 slides. And I'm gonna so that was a simple protocol, and a lot of questions that are coming up, I'll try and answer in the next 2 slides, but I'm gonna put it in the framework of incenting ISPs to do the right thing. We are operating in a strategic environment here, and ISPs are likely to cheat the system if they can. So in the next 2 slides, I'll describe my mechanisms for incenting the downstream ISPs to disclose the costs honestly, and I'll incent the upstream ISP to be sensitive to remote costs in the process. So incenting downstream ISPs to be honest about the cost disclosure, and the problem is simple to see. This is the same example as the last one, same set of costs here. Assume that the blue ISP is picking paths based on minimizing the sum added across the 2 ISPs. So if the orange ISP is honest about its agnostic cost, this is the path that would happen with the cost of 2 to the blue ISP. But if orange ISP was to play the simple trick as to inflating all of its costs by a factor of 10, this path would emerge, because let's say blue ISP is not doing any complicated routing, it's still adding the sum across the 2, this path would emerge. So how can we actually fix that problem? You look confused, sorry. Yes, for an individual path it does not make sense. Here's what I'm saying actually. So think of it like adding, for every flow that is picked based on adding the numbers. So what you want to do is just adding the so let me take a pen here. So let's say all the flows are routed like that. So by minimizing the sum across each path, you forget the plus sign. What ends up happening here is that the cost within the orange ISP also gets minimized. Yeah. Yes. Yeah. Right.
The blue numbers were number of hops, and the orange numbers were number of milliseconds.
Yes.
They're completely incomparable.
So let me make the same argument in a different way. So forget about adding. Let's say there is some mechanism using which the blue ISP can be sensitive to the cost of the orange ISP. Yes. Yes. So all I'm saying is adding is one simple way to do that. If you just add and pick the minimum path, automatically what happens, let's say all the paths, these are 3 different flows. All you want is this dash cost, or the cost of the orange ISP, be minimized between the orange cloud. And by picking each individual flow that minimizes this sum, ends up achieving that effect.
So like
Yeah.
example here is saying 1030 and 110 inflated. What if they're not inflated? What if the guy is actually using units actually needs to end up 1030 and 110, honestly?
So I'm assuming, yeah. So I'm assuming some sort of equal partnership in this Barter. And I'm going to, in the next step, I'm going to normalize these costs such that both these ISPs end up being some sort of equal partners in the Barter. And what the evaluation, I have in my backup slides, I have an evaluation that shows by just doing that, both ISPs actually win in the process. So the problem of fixing this inflated cost is basically what I just said, to normalize the cost such that both ISPs are equal partners in this Barter. That we were arranging independent bilateral Barters, and this is what we are going to do. And how this would manifest itself in the system is that, let's say, add up both the costs to unity. So this is what would emerge in the system. I've divided this by their totals. Venkat. Mm-hmm. Reduced. Yeah. Right. Right. Oh, it's not minimized. Yes. So let me try and get your question. Objective as in?
cannot minimize both the sum of the oranges and the sum of the object,
Mm-hmm.
right?
So objective would be to arrange a
And then at the same time, you can't combine the two of the oranges to get this.
yes.
So given that, what is your system?
The object. So what I cannot do in this case is to mathematically describe the objective function. What the goal is here to arrange a practical protocol using these two ISPs such that the cost of routing using this cooperative routing for both of them is reduced compared to selfish routing. Pareto optimality, yes, yes, right, something. Pareto optimality is a Pareto optimal solution from, it's a game theoretic term. Pareto optimal solutions in the system basically mean that compared to any other solution, or if you move away from Pareto optimality, at least one ISP loses. So conceptually, this is something I'm like, by reducing obvious wastage in the system that happens today, I want to come to Pareto optimality in the sense if you move away from it, at least one ISP loses in the process.
Essentially, though, you don't actually have a proof of your approach achieves that. That's just
Under some analytic models, you can say, you can argue Pareto optimality.
Am I willing to accept it to reduce my cost by a penny if my competitor's costs are consequently reduced by 4 cents? I mean, yes, we both do better, but now they're going to have lower costs than maybe.
You bring up an interesting point about rationality model. The only data point I have so far on what the real rationality model in terms of ISP cooperation is basically we're talking to Verizon, and they are very interested in doing that. And their interest comes from basically optimizing for traffic such as voice over IP or VPN traffic. These like are cash costs for these companies. And today they cannot offer voice over IP or VPN services that span networks. So by arranging like running some sort of protocol like that, it enables them to do that. So if it brings a lot of benefit, they might. But that question is actually an interesting one to say what. Yeah. Oh no. So Verizon wants to Verizon. So Verizon and one of its partners would use this. So that argument also holds like like think of Verizon and Verizon Prime would use it in the sense they are coming at it from a perspective that if we use it, our routing paths are optimized, and as a result, we can make more money from our customers instead of worrying about basically. I think routing. So ISPs are competing, but today what ends up happening today, routing is not the domain in terms of where that penny pinching plays out in the system. So what's ended up happening with normalized cost is basically we return back to the same routing pattern as before. So what we've done with this cost normalization actually is more than helping ISPs to have an equal cost range. By giving them each $1 to distribute over this cost, what we've done is made Wiser somewhat robust to strategic planning or to strategic interest. For instance, the only way for an ISP now to increase or artificially increase the cost of one of its path is by decreasing the cost along this other path. And there's an incentive to not do that, because once an ISP does that, the actual path the traffic might end up taking might actually be worse, just because it's lying about its costs in the system. And in effect, both like empirical evaluation over realistic topology and traffic patterns, it shows that we've reduced the degrees of freedom in the system so much that the amount of gain you can have by lying about your cost is not much. And yeah.
By normalizing this way, you have some link between the exceptional path, the routing what it's going to do is force all of the reasonable paths into a really tiny range and wash out. Does that make sense?
So the other thing to note is there would be, if an ISP is really hurting along this one path, there are actually like multi-ISP paths in the system where the traffic can go from. All I'm saying is that once you arrange that these two ISPs are equals in a barter, you basically are stuck with those kind of situations in the sense like I've given each ISP $1. You can arrange this $1 the way you want. I can arrange this $1. So this does give you a mechanism for arranging arranging for all traffic to go away from main is a thing, and other paths would be used, which you could argue is basically fair. This ISP, if its key goal right now in terms of its objective function is to avoid traffic going over the main link, and it can do that by just assign a higher cost to the traffic going to main or the link between whichever link is overloaded.
It almost seems like they're breaking the do both in this world off in a way that make
You mean the main link like
you have one that costs you 100,
uh-huh
and one that costs you 1 and one that costs you 2. When you normalize it, what
yeah
you're going to find out is that the cost of that looks like 98 for one,
mm-hmm.
0.98 for one, and then 0.0
right
something.
right
And as a result, there's almost no differentiation in cost between the two.
But the thing is, like in terms of overall objective function that the ISP, this particular ISP, with that cost structure is trying to do, it actually ends up achieving, because the difference between 0.9, the difference between the original cost 1 and 2, it doesn't care about as much as what it cares about in terms of the real cost that is 100, right? So if it has a yeah.
But it still costs it twice as much to route it over the 2 as over the 1. So what that network really wants to do is arrange to have no traffic over it, or almost no traffic over it,
uh-huh.
and most of the traffic distributed over the 1 and not over the 2. But you smashed it into such a tiny value that you're then summing that what happens is it's probably better for the network to just make the main go away.
So
And that
right.
can't be right from a global perspective.
So there
cannot influence better.
No. So you're right. So there are actually contracts between ISPs. So the main link would still be announced. So think of the other ISP. Let's say, so there is a very minor differentiation between those two links, which are between the link that is 1 and between the link that is 2. Think of the other ISP's perspective. So let's assign numbers here, for instance. So if this is 100, this is 1, and this is 2. Or let's say 100, 2, and 1. So you're worried about that you lose the distinction, you lose the differentiation power between these two interconnections. So what I'm going to say, if these two links are the same for the blue ISP, that distinction would still remain, right? If yeah.
So the fact that the factor is too different in the link, once you put it in normalized land, it's a different, a linear difference between 0 and 1.
Uh-huh.
Which means any advantage in the blue side is going to go to
In
fact, so think
yeah.
this way too. You've got a link. You've got another link from the outside of the Artist cloud to that cloud.
Yeah.
Whose cost is infinite.
Sorry, could you repeat that?
I'm saying if you're trying to extend the model that Phil's got here.
Uh-huh.
What if one of those paths, if it's extraordinarily expensive to get to that bound?
Okay.
This cost is effectively infinite, right?
Okay.
You have, individual humans running packets down.
Right.
Yeah, carrier pigeon that, right? So one thing you could do is you can say, we're not actually going to use the carrier pigeon that, so we're going to call this, we're just going to say it's not there. And that should be equivalent to saying that we're going to assign a really, really, really high cost.
Mm-hmm.
Because it's, it's really high. But if you did assign it a really high cost, as Bill says, you would drive down all of your other
Right.
approximately zero.
Yes.
And that's not right, because now you're throwing away, by adding a little bit of network capacity, by actually sticking the carrier pigeon to it, you've actually made everything else dramatically worse. Don't be willing to discriminate. So let me propose a moment.
Right.
What if we, rather than having higher numbers be bad,
Mm-hmm.
bad, what if lower numbers are bad? What if you assign a 0 or 0.00001 to carrier pigeon? 0 means you don't have it. 0.00001 is carrier pigeon. And then you try to, rather than minimize your cost, you try to maximize this thing.
Right.
Then you wouldn't lose it by adding a little
I see.
capacity. It doesn't take much away from your sum. I'm not sure if this actually works conceptually, but if it stands in contrast to what you have now, where you've got this funny case where really low balance or really, really undesirable nets actually hurt your global performance. You have to make a decision somewhere to say, if we just won't include this at all, rather than having it
I see.
I think the fundamental problem here is that you're trying to have one guy make value decisions about the other guy's thing. If you, where you were before you started this evil plus sign.
Right.
You were in a position where one guy could rank order routings for the other guy, but they couldn't directly compare them. And so if you came up with a system where I would make a proposal to you that says, I'll switch these two flows, which I know will make it better for you. Would you like to make a counter proposal?
So conceptually, I wanted to do that. The challenge for that, I have a paper with this NSDI does something similar. Instead of like normalizing like that, it proposes that the cost be within a fixed range, and it kinds to arrange that kind of a barter. And the challenge for that is I don't know how to take that conceptual framework and develop it into like a simple protocol that could go into the routers today. And maybe we can talk a little bit more about that. Yeah. Right. Yeah. Okay. So here's another trick. Yeah.
You're not mandating the ISP to normalize exactly what you're doing. You're not saying, an example, you can community out without conditions. For example, you take the example, you're not mandating that the link is really that. It's going to now look like 0.0999 at the end. Is that right?
Let me. So in terms of implementation details, that normalization happens actually conceptually. What in terms of what gets exported actually are like just the costs that are pre-normalized cost. Yes. Right. Yeah. But the point you brought up was interesting actually. I need to think a little bit about it. Thanks. Coming to the flip side of the problem, how do you incent an ISP to be sensitive while selecting paths to be sensitive to remote costs? And the problem here is simple, that currently, again, if you're choosing paths in a sensitive manner, this routing pattern might emerge. But there's nothing in the system so far that says that, well, the orange ISP is just going to ignore everything that the blue ISP tells it and keep choosing paths selfishly and keep choosing paths that are in the best interest that are basically locally optimal. So the fix to that is using basically a sort of like a virtual payment mechanism. I'm going to propose that the ISP that is sending the traffic makes a virtual payment to the downstream ISP, and the payment equals the cost advertised multiplied by the size of the flow. So here's the intuition here now, that there would be a rough balance of payment across the two ISPs. The way we've normalized the system, the average cost that is announced across this ISP boundary from both sides is the same. Given that these ISPs are exchanging a lot of flows over an extended period of time, what you would expect, that average payment per byte would emerge. And I'm going to leverage this expected average payment and have ISP sign, basically add a clause to the existing bilateral contracts that says that, okay, the payment I pay you within, let's say, a period of month versus the payment you pay me within a period of month should be roughly equal. Otherwise, something weird is going on. Sharad? Per destination. Right. Kind of like BGP. Sorry?
They have two flows, and they were able to both improve their cost by flipping the flows. The case you're trying to handle is where one guy says, sure, I'll move that, and then just doesn't.
Yes. So right. Well, there's a little bit of verification problem here in the sense of that the blue ISP, for instance, imagine a scenario where the blue ISP does not know what is locally optimal for the orange ISP. Right. Yes. So in terms of like what the sender's costs are. So this kind of like helps you with that. That I'm assuming a system that these ISPs are exchanging lots of flows within all nodes in their network to within all other nodes, and the average payment they end up paying would be the same. So without knowing, so the blue ISP in this case, without knowing what's going on, is actually able to achieve that. Here, Sharad.
Can I send bogus traffic to try and track costs?
Yes, you can. But I'm talking about payment per byte is one thing, but the bogus traffic problem even exists today. You can send bogus traffic to maintain your peer engagement.
Today, there's a per byte cost involved. We're talking about two ISPs that have a peering agreement, right? Where there's no change.
No, okay, so let me try and understand your attack. You send bogus traffic to, so that means you send, that doesn't change payment per byte, right? You send bogus traffic through the cheap link.
Yeah, I send bogus traffic on a link that I claim is very expensive for me, but it's very cheap for you. That way.
Wait.
Yeah, above the credit.
No, so you send,
So
sorry.
I have a path that I say is very expensive, right? And I'm sending traffic to a destination in yellow ISP that.
No, so the thing is, sender is not announcing its cost. Only the destination network is announcing its cost. Venkat, you had a question? Yeah. You mean the ISPs have just one interconnection?
Again, if you go back to this normalization thing,
Uh-huh.
say I can receive traffic only from one of these for whatever reason.
Uh-huh.
The others are not enough. But it's like
Okay.
No, but what happens to the cost system? I mean, basically, the cost is 1.0 in one direction. The other direction is always less than 1. So the difference is
There's no incentive for Barter on one side. So whichever the unidirectional, you have only one of them in.
exactly. So then the difference is
No
going to
incentive to
Y-
change.
Yeah.
There's no incentive to change at all for anyone that can get
Some people do not have to change the
In your models, have you assumed that all the links are bidirectional?
Yeah. I mean, I don't know if they're unit. Actually, the assumption is not. The assumption is that for Barter to happen, there should be bilateral traffic exchange, and in each direction there be more than one link.
But it's not required that
It's not required that every single interconnection in there be bidirectional. Yes. Then there's no incentive to Barter whatsoever. That's true. Oh yeah, totally. Yeah. So just quickly revisiting this example, if the Orange ISP continues to pick selfish paths, it'll end up paying more money, which could hurt monetary penalties. And I just want to point out this contract is actually not very complicated. Like I pointed out, it's very similar to what large ISPs have today by themselves. Like that bounds the traffic ratio. I'm kind of adding another clause very similar that lets bound the average payment per byte. Quickly extending Visor to the multi-ISP case. From this point onwards, it's rather straightforward. ISPs now add on this agnostic cost while announcing paths to the other. The recipients would normalize this cost based on the guiding principle. C1 becomes C1 prime, and it's just basically a normalization factor such that the costs should add up. Basically, Orange normalizes such that its cost, the sum of its cost and the sum of Green's cost is the same. And while doing that, and while transferring the destination further, one of the mechanisms while announcing to the blue ISP is to add up these costs, and which is how bilateral barter. Even though there's no contract between blue and green, blue in some sense indirectly becomes sensitive to the cost of green ISP because of this bilateral contract here that makes the Orange ISP announce that particular cost. The blue ISP would select a path out of the multiple ones it gets, and ISPs track virtual payments in the system. A quick word on deployability. I'm not going to go into detailed message level details, but people familiar with internet routing would know that the protocol itself looks fairly similar to BGP. The added tweaks in there are virtual payments and normalization, and there are some lightweight mechanisms using which you could implement those. And the other thing that really helps deployability for Visor, it's leveraging existing ISP contracts. I'm not changing either the contractual structure of the internet. They are still independent and bilateral. At the same time, I'm not changing the charging model of the internet. Today in the internet, both sender and receivers of traffic pay for that. Like Microsoft, if it has an ISP, it would pay both for sending and receiving traffic. And I keep that the same, which is kind of unlike all other protocols I know of, cooperative traffic management. The third thing that helps actually with deployment is that we can start with two ISPs. Even if two ISPs, only two neighbors deploy it, we'll start seeing benefits right from the get-go. The early adopters of technology don't have to wait for the others to catch up. And it's perhaps because these reasons, like I pointed out, there's great interest for, like, we are collaborating now with Cisco and Verizon, and there's interest in a test deployment of the internet, in the internet of this particular protocol that I'm working on these days when I'm not traveling. Finally, quickly, got 15 minutes to finish evaluation. I'm going to quantify, basically empirically evaluate Wiser. And the two key questions I'm going to try and answer is what is the price of anarchy in the internet, which is recall that difference between socially optimal routing and the routing with anarchy. The other question I'm trying to answer is what is the price of autonomy in the internet, routing that emerges from Wiser versus socially optimal. And in doing that, since socially optimal requires that ISPs have an equal, that ISPs have the same optimization criteria. So the criteria I'll focus on is path length. When focusing on path length, what you want is good performance for all flows, so that there's no more need for manual tuning that happens today. And I'll evaluate it based on that. And I've experimented with some other metrics. And some other factors that you might care about in terms of evaluating Wiser, but I'm not going to talk about that, but I have some backup slides if you guys are interested in any particular aspect. Answering any non-trivial question about the internet is basically non-trivial. We can't just go ahead and deploy what we propose in the internet. At the same time, there is very little data available. So at a high level, my approach is to use measured data when it's available, and to augment the measured data using known properties of internet routing. So in particular, I collected, as measured data, as part of my earlier work, I collected topologies of ISPs, what these look like. So these are two examples here. And the model I'll use for this particular evaluation is that path length, or the distance within the network, can be approximated using geography. So the length of this particular link is basically determined by its geographical endpoints. So here's the first result, price of anarchy. Bear with me while I try and explain this graph quickly. X-axis here is the path length inflation. So a factor of 2 means the path has gone from 10 milliseconds to 20 milliseconds. And this is the difference, how much paths are inflated with anarchy, which is like very close to routing today, compared to socially optimal. So this factor 2 means a path or a flow that took a path that was 10 milliseconds when you route in a socially optimal manner is taking 20 milliseconds in this particular case. And the y-axis is basically complementary CDF. So this is to say, this point here is saying about that 5% of the flows see an inflation of more than 2. So two things stand out here, that most flows are actually fine. So you see that this table here actually summarizes the graph, sorry. So what you see is that the common case is actually fine. There's no inflation at all for the common case. And this is contrary to previous theoretical results we have on price of anarchy that claim that the cost of anarchy in the internet in this setup can be a factor of 3. This is the average case, and which just kind of goes back to my motivation for using real topologies, because often is the case that the real network looks a lot different than theoretical models because of the complexities. But what you do see is is that there are a lot of paths that are inflated. So 5% of the paths are longer by a factor of 2, and there's 1% of paths in the system that are longer by a factor of 6. And this length inflation here is not limited to short paths. There are long paths also in the data set that see a huge inflation. Don't. Yeah. Yeah. I don't know, but I don't know if this would answer your question. In terms of a typical path, for instance, would traverse about, let's say, roughly 4 ISPs. 2 of them would be large, and spread of a large ISP, taking North American paths, would be about 50 milliseconds. Does that give you enough input? I don't know offhand the answer. Oh, I see. Yeah, I think that average number, if I was to plot like, right. So this I guess 50% would be kind of like the median. I don't know if you're getting at the average or the the mean. Okay. Oh, I see. Okay. Right, right. I haven't done that. Yeah. Uh, right. Uh, Okay, so the thing to note here is that these are the paths that are not automatically optimized today, and these are the paths that require manual optimization on part of operators. So the point I'm trying to make is the price of anarchy today in the internet is high when you consider path length, only because operators have to go in and tune these paths when they hear things from their customers. And the goal for Wiser then becomes how well can it optimize this tail in the network. So the red line here is that of Wiser. And the graph is in a very similar format and replicated the line for anarchy, and similarly for the table here. So what you're saying is Wiser is coming very close to the socially optimal. 1% of the paths that are inflated by 6 are inflated only by a factor of 1.5 in our system now. And from a theoretical perspective, this result is kind of like, leaving apart numbers, this result is kind of satisfying on 2 counts. One is that competing interests are not causing much efficiency loss. The way we structured Wiser, it was supposed to be win-win. And it is win-win when you consider it over this over internet topologies. Socially optimal, on the other hand, is not win-win. Socially optimal is win-lose. While computing socially optimal, some ISPs actually lose out. So what we've seen with Wiser, you can develop protocols such that competing interests in the system can be effectively accommodated, and there's not much loss in global efficiency. What this result also shows is that multilateral barter that I talked about in terms of potential efficiency loss is multilateral barter, at least for these metrics and topologies. Multilateral barter is not required, because even with independent bilateral barter, we are coming very close to what you could hope to achieve in terms of the optimal in the network. Let me try and give you a quick insight into why these results come about and what is the nature of the internet topology that enables these results to come about. The hope is the following, that getting some insight using a simple analytic model will not only understand something about the internet topologies, we'll also understand what kinds of situation Wiser can help you with. So here's a simple model of internet routing. Assume that, again, 2 ISPs with a number of interconnections between them. The average cost, using some metric, let's say distance, between the blue ISP is 1. By average cost is 1, I mean like cost of carrying traffic from a node within the network to an interconnection. What is the average number? Similarly, the average cost inside the orange ISP is R. So I'm not going to claim that this is an accurate model. All I'm saying, this particular simple model actually predicts a lot of the results I see, including what happens if you change the number of interconnections, and it also provides some insight. So here's what's going on. This graph is plotting what the gain in social efficiency would be relative to anarchy for both Wiser and socially optimal. So what we see is that when R is close to 1, that ISPs have similar costs, Wiser is actually close to the socially optimal. But after when the differences in the cost of the 2 ISPs begins to diverge, socially optimal is more efficient. So why is socially optimal more efficient as R goes high? And the answer kind of lies in this particular. These curves are plotting the efficiency gain for individual ISPs in the network. So what you see with the socially optimal, ISP-R gains in efficiency, but ISP-1 begins to lose. So we are shuttling all of the traffic across our cheaper ISP, and it kind of loses in the process, which is what I meant by socially optimal being win-lose in certain points. But what you see with Wiser is that Wiser stays win-win, that both ISPs win. So end result basically is the following, that when the ISP costs are roughly similar, Wiser comes close to socially optimal, and when they're largely different, Wiser is less efficient, but it stays win-win. And which is why, like with using Wiser, ISPs of different sizes and different cost structures can cooperate without the fear of losing. At the same time, what we saw in the empirical results, that Wiser comes very close to socially optimal, which kind of like goes back and feeding from the model to reality says that internet topologies R must be close to 1. In hindsight, actually, when I found this out, the result makes sense, because competing paths in the network are offered by ISPs, like tier 1 ISPs, that have similar structures. When you talk about like AT&T and Sprint, their spread is across North America. So R for those particular ISPs is not very high. And it kind of goes back into how the internet topology is structured. in there. So R in the internet topology in terms of the to a very first order is similar, is if you believe this model and feed it back into the internet. I want to provide you a glimpse of some of my past work. The pieces of work I've chosen also tackle competitive interest at some level. And the closely related one is what I hinted at before, cooperation in multi-hop wireless networks. And the problem is the following, that multi-hop wireless networks, nodes are expected to relay packets for each other. But what happens if a node does not want to relay packets is that it can hurt the performance of the network, and at the same time it can partition the network. So I have a protocol called catch that encourages cooperation in such networks, which I've implemented in Linux, actually which kind of makes it like the only wireless incentive protocol to have a real implementation. I've also evaluated catch on 802.11 testbed and found that it effectively counters cheating or dropping packets in that particular domain. Getting back to the internet context, one of the problems that is especially challenging when it comes to having competing interests or independent parties in the system is what happens with debugging. So debugging becomes harder because ISPs have an interest in hiding information. In two separate pieces of work, what I've shown is that it's possible to write effective diagnosis tools and perform diagnosis using just the information that ISPs reveal as part of day-to-day operation. In particular, I've developed and implemented a tool called Tulip that locates where the losses and reordering and congestion happens in the network. And this tool is actually has been used by several ISPs, and one of the vendors is thinking about implementing its techniques in our commercial offering as part of network diagnostic suite. The other thing that I mentioned this result earlier on, which is a study of the first ever study of configuration errors in global routing to quantify their impact and understanding what kinds of bad things happen. And this has led to an improvement in the configuration practices, and we also discovered actually a major bug in the Cisco routers, and the bug's been fixed now. The other thing that's challenging is in terms of when ISPs are trying to hide information is to get a sense of the structure and operation of the internet, which is important to understand, not just for the purpose of understanding, but also to evaluate and develop new protocols. So I've developed systems called Rocket Fuel, and I've also developed new techniques that enable us to uncover this information. And actually, the data produced by these two pieces of work has become the de facto choice of information that many researchers have since used in evaluating whatever their new research. To conclude, I started my talk with the observation that many network systems today mix cooperation and competition. And the reason for that is simple, that any large-scale system, the infrastructure is often owned by many competing parties, that there's no single organization that owns all of the infrastructure. What can happen if these competitive interests, if they're unmanaged, they cause performance and reliability problems in the network. So at the same time, we don't have practical protocol design abstractions that enable us to tackle these things, which we have to tackle because these are here to stay, as I've argued. So in the domain of internet routing, what I've shown is that there are practical designs that can effectively manage these competing interests. Wiser in particular, it preserves ISP autonomy, lets them take decisions that is in their best favor, and at the same time in doing that comes close to socially optimal. And the key piece that Wiser leverages in doing that is the contractual nature of the internet and the topological structure of the internet to some degree. Kind of like a satisfying result, because what it shows that we can accommodate all the competing interests in the system using a practical protocol with not much cost in terms of efficiency. So in other words, what I'm saying basically is that the price of autonomy in the internet is low, and there are practical mechanisms, cheap mechanisms to implementing autonomy are also low. And that concludes my talk. Thank you. Questions? Sharad.
There's some questions?
Yeah.
Okay. You see this is not only between tier 1 ISPs in your example, but also between large ISPs and smaller ISPs?
I would hope it does. I mean, the protocol itself works across any number of ISPs, and yeah, I see no reason why it would not be used. But right.
That you showed,
Mm-hmm.
you kind of got the sense that these are additive metrics, and you're trying to target delay or hop count.
Mm-hmm.
So would this work well, where one ISP is trying to optimize for utilization versus another one that is trying to optimize for delay or hop count?
Yes. The reason, I'm saying yes, just based on empirical evaluation, which basically the experiment was set up as follows: one ISP is trying to minimize delay, one ISP is trying to minimize delay in its network, and the other ISP is trying to minimize congestion in its network. So what you see, what ends up happening in that particular domain is the ISP that wanted to minimize congestion is able to minimize congestion, and the ISP that wanted to minimize delay is able to minimize delay. The thing that goes wrong in that particular case is that what happens to the end-to-end path. Because ISPs have incomparable metrics, the end-to-end performance of any given path you cannot tell, which you could argue is kind of like a fundamental consequence of ISPs hiding information from each other. But going back a bit, so what happens in reality, even any congestion-based metric has a delay component to it. That, I mean, most of the formulations for minimizing congestion are sensitive to distance, because once you're done minimizing congestion, you want latency to be minimized. So once your metrics are kind of latency guided like that, and they get some sort of common basis to them, then end-to-end path performance also increases, which is what you see using these results. You look confused. So let me summarize that. If the metrics are totally incompatible, each ISP is able to achieve its own metric. And end-to-end path performance would be better if those metrics have something in common. Yeah, okay, cool.